In Part A and Part B of this, I spent nearly a half hour making the case for testing capacitors that you are putting into equipment, not necessarily testing the ones that come out. Now, of course, for purposes of just figuring out how bad the capacitors are, there's nothing wrong with testing the capacitors that you remove. But the reason that I am fairly convinced that you need to test the capacitors that before you put them in is the fact that I've seen the effects of a bad capacitor, sometimes because they failed, and sometimes because a bad capacitor was put in the circuit, sometimes by me. So over the years, I've learned that, for example, if you're replacing this electrolytic in a power supply, this is a vintage Zenith receiver that you see here, or the circuit from one, and let's suppose that you replace this with a defective capacitor, that is, one with high leakage. One of the problems that causes is there is excessive current drawn through this rectifier tube. That can have two impacts. One is it can cause the tube itself to fail prematurely. It's what happens is, as the cathode is used or overused, in other words, as too much current is pulled through the cathode to supply that leakage current, the cathode will actually begin to erode, and eventually the rectifier tube will have to be replaced. But, of course, that extra current also has to flow through this power transformer. And so you can wind up with excessive heating in the power transformer, which then causes the power transformer to fail also. So testing capacitors that you're going to put in power supplies for leakage is very, very important. Actually, if the value is a little bit different from that shown in the schematic, like it says 20 here, but let's suppose the one you have is 22 or 24 microfarad or even 15 microfarad, that's not going to cause as much problem as as a leaky capacitor. Also, if you are a believer in bigger is better and you replace this 20 microfarad, say, with a 200 microfarad, then every time that the set is turned on, excessive current flows through the rectifier because you now have to charge 10 times as much capacitor as you had before. Not only does that cause the rectifier to fail earlier for the same reason, in other words, a large capacitor here during the turn-on surge is just as bad as having a leaky capacitor. And once again, it can overheat the transformer and, in time, will cause this set to fail prematurely. Okay, that's power supplies. What about the rest of the circuits? Now, those are electrolytics. Why do we replace the paper capacitors? Well, let's take a look at the circuit here. And let's suppose that we're talking about the output circuit. Now, the output circuit has a coupling capacitor on its input. Let's suppose that we put a leaky capacitor in this location. That means that the plate supply, which is on this side, is leaking through to this side. That positive voltage eventually winds up on the grid of this output tube. Now, this is especially important for people who work on things like hi-fi amps and guitar amps and things like that, where these output tubes are often being run at significant current. If they're not biased properly, you not only will get premature failure in the tube itself, but you'll also get premature failure of the output transformer, because all that excess current that this positive bias is causing this tube to conduct, not only do the plates of the output tube start to get red, but also the transformer starts to overheat. And that can quickly blow an output transformer. So you may wind up, if you put in a leaky capacitor here, you very well may wind up having to replace your output tubes and or your output transformer. So once again, it's very important, and not just in vintage equipment. The same thing is true in transistor equipment. If you have a leaky capacitor there, it can upset the bias of the next stage. It also puts more load on the power supply, although normally in a case like this where there's a resistor in series, that's not a problem. This resistor may overheat if this capacitor leaks. But resistors are easier to find and fix. The big problem with leaky capacitors in circuits like this is that it upsets the bias of the following stage. So that's a second reason. Let's talk about this capacitor. If this capacitor, which is a bypass capacitor, is shorted or leaky, it's going to pull excessive current through this resistor. So when we are replacing bypass capacitors, it's equally important that we test them at or actually above the voltage they're going to be used. In old receivers, these were typically wax paper capacitors, and that's one reason that I pointed out early in this series that you really want to replace these with modern film capacitors. Film capacitors will last longer, but as I showed at the very beginning, even a brand new film capacitor right out of the box can still fail at voltage. And the reason is that most cheaper capacitors, and by that I mean those capacitors that have not been run through a mill standard control where they test every capacitor, they have been manufactured under statistical quality control, which means that most of the capacitors are good, but they're not all tested. So let's look at some failure mechanisms in capacitors and see why that they tend to fail. And as you will see as we go along, the dirtier the manufacturing facility is, the more careless they are in terms of their materials, and frankly, the cheaper they sell the capacitor, the more likely you are to get bad capacitors in a batch. So if you're one of these people who looks around for the absolute cheapest capacitor to put into an old radio, and then you don't test them, you're asking for trouble. You're probably also asking for trouble because the capacitors you put in are going to be failing themselves. But you make matters worse if you don't even test them before you put them in. So let's cut open these two capacitors, the electrolytic at the top and the wax paper at the bottom, and see what makes them tick, or more appropriately, what makes them fail. First, we remove the paper coverings, and I think you can tell from the fine surgical precision here why it was a good thing that I went to engineering school instead of medical school. It wasn't that I couldn't get used to liking the blood, it's just that, I'm no jeweler either. Inside the electrolytic is this aluminum can, but inside the wax paper capacitor or condenser is this wax plug, if you will. So now let's cut each of those open and see what's down inside them. Here I've sawed the end off of this aluminum electrolytic. And you can see a connector in there. So now I'm going to try to pull this out of the center. And here it is out of the aluminum center. And you may notice down here there is actually, let me get this a little closer, an aluminum strip that goes down inside, maybe a little hard to see because of the light. Let me try to get the light a little closer here. See if you can see down inside there. Basically, this aluminum strip is tied to the very base of the can. In other words, the outer can. And then here you have, to the center of this electrolytic, you have the lead that comes out through the cap or the plus side. Now I've laid it on this piece of newspaper. If you do this yourself, be aware that there often is some liquid electrolytic still caught inside these capacitors. It's the electrolytic that tends to dry out over time, but you can't depend on it all being gone when you take your capacitor apart. So right now there is a fairly strong odor of actually what smells like alcohol, but is the electrolytic that was on the outside of this. And there will probably be some still trapped inside. But don't do this on your good dining room table, because that electrolytic is caustic. And if you get it on your fingers, you should wash them off. It's probably better to wear rubber gloves and so on. But anyway, where we're going is to take a look now at the insides of this one, and then we'll do the same thing for the wax paper capacitor. And now I've cut the two contact strips so that we can get this out. You may notice up here on the paper some little wet spots that are from the electrolytic. Once again, that's the reason why you should protect the surface that you're laying this on. So now let's cut this open and see what it's made of. Now I've unrolled the electrolytic, and you can see the foil roll on the inside. And of course, as you keep unrolling it, there is a little bit of electrolyte down inside here. Pardon the reflection, the glare. Yeah, I'm wearing gloves. I'm not a complete fool. Yeah, sometimes I even read the manual. At any rate, the way that this is built up is there is a layer of foil, and then the paper on the outside is impregnated with an electrolyte. And then by rolling this up, you basically produce a very large capacitance. So instead of having two plates that just fit together like this, by rolling the plates inside one another, you get a much larger total capacitance in a smaller area. So we'll set this aside for a second, open up that paper cap, and then we'll talk about the failure mechanisms. I wasn't able to do as neat a job of unrolling this wax paper capacitor, but nonetheless what you can see there is this was rolled over or inside this, which there you can see the foil that's on the inside, and then the wax paper on the outside. Now, unlike the electrolytic, this paper is only impregnated with wax, and so this is not an electrolytic capacitor. It's actually just a dry wax paper capacitor. So now let's look at the materials that these capacitors are made out of, and what the failure mechanisms are. So how do defects form in new capacitors? Well, the first thing is, and here I am going to simulate the way a capacitor is made by, this is a piece of aluminum foil, this is a piece of actually plastic coated paper, not wax coated paper, but the principle is the same. Now let's suppose that during manufacture there is a problem with a pinhole, and of course I've simulated this with a lot larger hole, but nonetheless a pinhole in the paper. That pinhole then provides a conduction path between the foil on one side and the foil on the other. So you might ask, well, how do you get pinholes? Well, part of the problem was that prior to the space program, and we'll talk a little more about that later, the companies that manufactured capacitors, it was almost like a garage shop operation. They didn't have any quality control on their materials at all. So they just would buy paper, coat it with wax, aluminum foil, roll it up, put it together. Later, during the space program, there was an actual attempt to find out what went wrong when capacitors failed, and so they started taking apart capacitors that had failed under test. And what they found was that almost all of the failures could be traced back to pinholes in the waxed paper. So initially, they thought that some of the new plastic films that were being developed would make a difference. Well, part of the problem is that it depends on the plastic. Now, this is polyethylene. It does not make a good capacitor dielectric for a lot of reasons that I won't get into, but one of the problems with many plastics is, while they appear to be very solid to most people, and because the molecular structure is such that water won't go through them, they assume that, you might assume that they're impermeable, but they're not. Actually, electrons have very little problem flowing through certain plastics, and unless the plastic is thick enough, then you do not have enough insulation between the two. When you start to apply higher voltage, the plastic itself will break down, just like the pinhole paper would break down. So that's easy. All you have to do is make the plastic thicker or the paper thicker, and you don't have that problem. Well, the trouble there is that, remember, you're rolling these things up, and as you roll them up, the thicker the plastic, or the thicker the paper, the bigger the capacitor becomes. So, to provide a lot of capacity in a small space, you need thin paper. Thin paper means you have pinholes. Pinholes means you have failures. So, one of the big advances that the space program brought about in the 1960s was that instead of simply buying materials and rolling the capacitors and then testing the capacitors, often they found you had to actually test the materials themselves. So today, most good manufacturers run their plastics through a screening process to find the defects. But a second problem is, if you allow grit to get on the plastic, then when you roll the capacitor up, that grit serves as a failure point. In other words, it presses on the plastic, and the plastic will actually migrate away from that little bit of grit. So a second thing that they had to do was to start manufacturing capacitors under conditions in which there is no dirt. Not as clean as a clean room, a modern clean room for integrated circuits, but nonetheless a lot cleaner than the way they used to do it back in the 30s and 40s. So those are how capacitors fail. The cure was to screen the materials that go into the capacitors. Now, a lot of people think that capacitors that are manufactured today are tested. A lot of them are not. Instead, there is often a statistical sampling of capacitors that are tested, and by that I mean fully tested under load, tested for all sorts of other things. So the problem with statistical testing is you may be the victim of the one that didn't get tested. So I encourage you to test every capacitor before you put it in a circuit, and test it under full load. That is the maximum voltage that it's going to take. So I hope I haven't harped too long on the value of testing capacitors before you put them in circuits. Whether you're working on modern equipment with switching mode power supplies, or you're working on vintage equipment with linear power supplies, whether it's tube or transistor, testing the capacitors before you put them in circuit is, I think, an essential part of repair and or restoration of a piece of equipment. So what is the bare minimum you can get by with if you don't want to spend a lot of money? Well, you don't really have to get something as fancy as that Sencor LC102 or the LC103. For most of this, in fact, if you are going to be doing work just in transistor equipment, a simple LCR meter like this that will check the capacitance and ESR is all you really need. If you have a multimeter that can read capacitor value, one of the things you might want to consider is adding a leakage tester like this homemade unit on the right over here. This is a unit that I first showed in my restoration series on the Hallicrafters SX62. It will test at 100 and 200 volts. It will also, with a transformer like that you can add for about $5, go up to 200 and 400 volts. So that, for leakage, some way of measuring capacitance, and if you're working especially on any kind of switching circuits, and that includes switching power supplies, some way to measure equivalent series resistance. I hope this has been helpful, and I hope that you have enjoyed watching it. Once again, at some point, I hope to be able to dig out all of my old vintage capacitor testers and maybe do a little mini review of those. But for now, have a nice day, and we'll see you in the future.